Let's consider the special case of tensor products of modules over commutative rings. So I'm going to assume now that R is a commutative ring and let M and N be modules over R. So recall this important thing we talked about before when we talked about bimodules. When you have a module over a commutative ring, you can think of M as both a left as well as a right module over R, but also as a bimodule over R. So in fact, M as well as N are both bimodules. It's actually an RR bimodule. Well, what's the bimodule structure? It's just the same action. So left multiplication action, action on the left is the given action. Action on the right is just the same as the given action, just think of it as multiplying on the left. Okay, and we had seen this before, that because R is commutative, this makes M into a RR bimodule. Okay, now the point is, the tensor product, as we discussed last time, if M is an RR bimodule and N is an RR bimodule, this means that the tensor product becomes, again by the same token, this R, so this is tensor product over R. So this R and this R sort of are used up when we construct the tensor product, and what's left is really this. So it's an RR bimodule, becomes an RR bimodule, and what's the structure or scalar multiplication here? So here's what we know. If I take an element from R, then the left multiplication, so when it acts on a generator or a decomposable tensor M tensor N, R acting on M tensor N by definition is Rm tensor N. Okay, that's the left action if you wish. The right action similarly, M tensor N acting on S, well, by definition is M tensor N acted upon by S on the right, but as we just defined, for commutative rings, the right and the left actions are the same. So this is just M tensor Sn. Okay, but the point now is that this tensor product operation is R balanced, which means that if I have a scalar on that side, I can sort of bring it past the tensor product to the other side, right? So what this gives me is just this is just MS tensor N. Okay, so this is another way of thinking about it, but MS is the same, remember, as SM, because that's the definition, tensor N. Okay, in other words, what this says is that, so maybe if I replace the S by R everywhere, so observe, if you put R equals S, then these two actions are actually the same. In other words, right multiplication by R and left multiplication by R on the tensor product is actually given by the same thing, okay, which is, you can think of it either way. So even though we say it's an RR bimodule, in some sense these two structures coincide. So it's only an R module, if you wish. It becomes an RR bimodule, but left and right R module structures coincide. Right? That's what we have seen above. If you put R equals S. So therefore we view it only as an R module. So we view M tensor N as, it's enough to say it's an R module. Okay, you can think of either of the two formulas as giving you the scalar multiplication. Think of it either as Rm tensor N or as M tensor Rn, if you wish. Okay, now what more can we say? So in this context, when R is a commutative ring, the tensor product, not just does it have the defining universal property. So recall we more or less defined the tensor product as a Z module with a certain universal property and so on. In this case, there exists another universal property. Okay, so this has another universal property, which is sort of more useful in some sense when we are talking about commutative rings, and this is given by the following proposition. So let M, N, P, K maybe be R modules. So R is commutative. Okay, and let F from M cross N to P, M cross N to K be R bilinear. Okay, now what does this notion of R bilinear mean? So we have only talked about so far of Z bilinearity and the notion of R balanced maps. Okay, this is sort of a little bit more than those notions. So what does R bilinear mean? I.e., you say f of, well, it's Z bilinear. So f of M1 plus M2 comma N is and the other way around, M comma N1 plus N2 . Okay, this is true for all M's in M and N's in N, but in addition to these two, we also demand that if you put a scalar R, okay, then you should be able to pull the R out. Okay, so observe on the right hand side, what do I mean by pulling the R out? The right hand side f of Mn, recall, is an element of K here. Right? It's going to the module K, and K is an R module. So there I know what scalar multiplication means. Okay, so f of Rmn is R times f of Mn, and this should also be the same as f of M comma Rn. Okay, so now I want this to be true for all M. Okay, I also had M1, M2 on the previous page, for all N, N1, N2 in N, and for all scalars R from the ring R. Okay, so any map which satisfies these three properties is said to be, so I need three properties, 1, 2 and 3, such a map is said to be R bilinear. And observe, this is the usual notion if you have looked at things like vector spaces and so on, which corresponds to the case when R is a field, then this is exactly what we call bilinear maps between vector spaces. Okay, so given such an f, okay, let f be R bilinear. Okay, then what does the proposition say? It says there exists a unique R linear map. Let's call it f tilde from M tensor N over R to K. Okay, such that the diagram commutes. So what diagram commutes? Such that f tilde composition alpha is f, and what is alpha? Where alpha is the standard map from M tensor N to M cross N to M tensor. Okay, so this is the usual map. Okay, in pictorial terms, this says that you take M cross N to K. If you are given a bilinear map F, then look at the standard. Says that this map F gives rise to a unique map F tilde. The key point here is that this is R bilinear, whereas this map F tilde that we have defined is an R linear homomorphism between these two R modules. Okay, so let's prove this. In some sense, the existence of the map itself comes from the usual property of the tensor product. So let's first look at that. So observe that an R bilinear map is automatically R balanced. Okay, so first I will reduce this to something before. So observe now that think of this k here, think of k only as a so think of k only as a z module for now. Okay, forget the fact that it is an R module. Okay, for now temporarily. Then I claim that the map F being R bilinear in fact implies that it is an R balanced map. Okay, claim F is actually R balanced. Okay, why? Well, the R balancedness, the properties 1 and 2 that you need for R balancedness are exactly the bilinearity conditions 1 and 2 that are satisfied. So these are exactly the two conditions you need for something to be R, the first two conditions you need. So 1 and 2 are the same as for R bilinearity. Okay, it's only condition 3 that's different for R balanced maps. So what is condition 3? We need that f of mr comma n has to be the same as, so the question, is this true? Is this the same as f of m comma rn? Okay, where r is in R and m and n are from m and n. So why does this follow from R bilinearity? So let us check. So what is the left hand side? Well, f of mr comma n. So what does mr mean? I'm going to do right module action by R, but recall the right module action is just the same as the left module action. Okay, and now by bilinearity I can pull the R out. So the last step is because f is bilinear, by R bilinearity of f. Okay, now let's compute the right hand side similarly. The right hand side is f of m comma rn, but then by bilinearity I know that I can pull the R out. Okay, this is the R bilinearity of f. So what this means is of course that LHS is equal to RHS. Okay, so in fact if a map is R bilinear, it's definitely R balanced. Okay, good. So what does that imply? It says now that we can use the universal property of the tensor product that we already proved. Okay, what is that? So on the one hand, m cross n to k, where k I'm going to only imagine is a z module. I have this map F that's given to me. I know it's R bilinear, but in particular that means it's R balanced. Okay, so I have the map alpha, m tensor n over R, and I know there exists a unique f tilde. And what sort of map is this? The usual universal property says f tilde is a z linear map from m tensor n to k, and f tilde makes this diagram commute. So there exists a unique f tilde z linear as in the diagram such that f tilde composition alpha is f. Okay, why is this? By the usual universal property, by the universal property that we already proved. Okay, and remember this universal property is actually even under the assumption that the ring is non-commutative. Okay, generally for non-commutative rings and for balanced maps, you can always find such a linear map f tilde which makes this diagram commute. But now we are saying if further the ring is commutative and the map is not just balanced but also bilinear, then f tilde acquires some additional properties. Okay, and the additional property is that it is R linear. So that's the only additional thing we need to check. Okay, so claim f tilde is not just z linear, it's actually an R linear map between these two R modules. Okay, it's an R linear map from m tensor n to k. Okay, so let's prove this. Now how do you check R linearity? Let's just check it on the generators. Okay, so I will take f tilde. Let me take a typical generator m tensor n. Okay, and I will hit it by R and see what I can get out of it. Okay, So, well, this by definition is f tilde of, so how do you take m tensor n and multiply it by r on the left? What's the r module structure? So, this is what we looked at in the beginning. How do you get an r module structure on, well, here it is, right? An r module structure is you can multiply, say, the first component by r, or you can also multiply the second component, solve the same, you give the same answer. So, let's use that. So, this is just Rm tensor n. Well, but what's that? That's just f tilde composition alpha of Rm comma n. So, since it makes the diagram commute, this is just the same as f of Rm comma n. And this is r bilinear, so I can also pull this out. So, it's r times f of m comma n. Okay. So, what this means is that f tilde of this, so what's the final answer? This is r times f tilde sorry, what did I want to do? Okay, so I just wanted to rewrite this. So f of m comma n is of course just m tensor n. Yes, that's what I want. Okay, so this property, so this equation here is where I'm using the additional property of f, because f is bilinear. Okay, so now what have I finally managed to prove? I've shown that f tilde, sorry, I should be a little more careful. So f of m comma n is the same as f is the same as f tilde composition alpha, right? So this is just r times f tilde alpha of mn. So this, sorry, there's an f tilde here. It's f tilde of m tensor n. Good. So look at this final equation here. So this says f tilde of r times something is r times f tilde of that. Okay. So this just tells me that f tilde is not just z linear, it's actually r linear. Okay. So that's what we set out to prove, that this map is r linear. Okay. Now, so one can in fact, define, and that's usually often how it's done when one only cares about commutative rings. You can just define the tensor product like this if you are looking at commutative rings. Okay. So if R is commutative, then you can say that the tensor product m tensor n is the object which has the following universal property, that whenever I have an R linear map, let's look at this, given an R bilinear map from m tensor n to k, it induces a unique R linear map from m tensor n to k. Okay. So this is now, this is sort of working inside the category of R modules where R is commutative, and this is often how it is defined. Okay, but this is very special to the commutative case. You can't make this definition if R is not commutative.